Hello, welcome to this 8th online session of the course Engineering Thermodynamics. So in our previous lecture, we started our discussion on the properties of pure substance. Today also we will continuing the same, and moreover, I have asked all of you to today keep steam tables ready with you. So we will try to employ steam tables for obtaining the properties of water in its different phases. Okay. So I'll take up from the portion which actually I was discussing in our last lecture. So in our last lecture, I have taken a piston cylinder arrangement, and then inside that piston cylinder arrangement, what we were having water in the liquid form at the bottom portion of the container. So here we were having some liquid water, and then in the top portion of the container we were having certain amount of vapor. Okay, so it means we were there in actually two phase equilibrium region. So particularly we were there actually in where we are having the combination of both liquid as well as vapor. Okay, so what we have considered, we considered that the volume occupied by liquid phase is VL, volume occupied by vapor phase is Vg. Okay, and also we considered the corresponding mass is mv and ml. Okay, then after that we have come up with some averaged equation for specific volume of our entire system. It means entire system means nothing but the mixture of liquid and vapor. So for our entire mixture we have come up with specific volume equal to nothing but 1 minus x times VL plus x times Vg. Okay, where this x is nothing but a parameter which is called as dryness fraction, and this dryness fraction is nothing but equal to mass of gas divided by total mass. Okay, so what we will be having, this whatever I am writing capital M, that is nothing but my total mass, that will be the sum of liquid mass plus gaseous mass. So now what will be happening, this x whatever we are writing over here dryness fraction, that will be nothing but the mass of gas divided by total mass. It means it specifies what fraction of vapor mass we are having in our mixture. Okay, so this particular equation, if you see over here, this 1 minus x term is nothing but it is representing the fraction of liquid phase. Okay, so this is nothing but mass fraction of liquid phase, and this x we are having as nothing but mass fraction of vapor phase. Okay, so mass fraction of vapor. So it means you can see that while we are defining the overall specific volume for this particular system, this overall specific volume V is something which is nothing but weighted mass average of the individual specific volume of the liquid and vapor. Okay, so the idea is that though in our within our system what we are having, this liquid portion is having some different specific volume VL, and vapor portion is having some different specific volume Vg, and we know because of the difference of specific volume, or I should say because of the difference of density, this liquid and vapor will not be staying as a mixture, rather vapor will be completely separated from the liquid part. So what will be happening, liquid portion will be at the bottom and vapor portion will be somewhere near the top. Okay, so it means if you try to see over here, we are not having any physical average value. Okay, so we don't have any physical overall value or physically average value which is actually the representative of specific volume. It means that if I say that V is my weighted average specific volume, I cannot say that everywhere within the system my average specific volume is this V only. Okay, so that is something which I cannot say. Okay, so what will be happening over here, we are saying that the liquid and vapor phases are having some individual specific volume. So if you see this VL, everywhere within this liquid portion we will be having VL, and everywhere within the vapor phase we will be having VG. Okay, so it means we are having the individual value of specific volume for liquid and vapor, but whatever we are getting from this equation, this is something which is the average quantity as a some magnitude representative for the system. Okay, so this is nothing but some representative for the system of our entire specific volume. Okay, now let me little bit elaborate this concept on our TV diagram, particularly in order to show how it looks on a liquid vapor dome. Okay, so I am considering temperature along ordinate and specific volume along abscissa. So now if I plot my liquid vapor dome over here, so what I am referring to basically, when I have this container where I have the mixture of liquid and vapor. So what I am trying to say now, that I am trying to say that whatever the vapor I am having, that will be having specific volume equal to that of this particular value, saturated vapor. So whatever VV I am saying, this VG I am saying, this VG is nothing but the specific volume of this saturated vapor state. Okay, and whatever VL I am saying, VL is nothing but the at the corresponding state specific volume of this liquid phase. Okay, so that is something which we have to consider. Now I have defined you the dryness fraction. So dryness fraction is nothing but it was the ratio of mg divided by m. So when we are on saturated vapor line, at that time our entire mass will be nothing but vapor. So it means this saturated vapor line is nothing but corresponding to dryness fraction equal to 1. So for this saturated vapor line, we will be having dryness fraction equal to 1, and this saturated liquid line is nothing but corresponding to the situation where we are having no presence of vapor. So it means mg is 0. So it means this line on the left of the critical point is nothing but represents x equal to 0. Okay. So similarly, if you now try to plot the multiple x lines, so you may find something like this. So this will be over here x equal to say 0.1 and over there x equal to say 0.9. Okay. So similarly, I will be having multiple x lines over here, which will be actually representing the different phase fraction values over here. Okay, so let me consider this as nothing but 0.2 and 0.8. So similarly, if you plot the multiple phase fraction lines, you can plot it over here. Okay, now what I have told you, that whatever the liquid vapor I am having over here, this whatever the liquid we are having, this liquid state will be having specific volume corresponding to VL, and gaseous phase will be having specific volume corresponding to VG. Now we are having this mixture. So let's say we are having any value of arbitrary any value of x. So corresponding to that value of x, if we are finding that V is our overall volume, so obviously that overall volume will be lying in between our liquid vapor dome. So this is our line of constant temperature and constant pressure. So over this line we will be having actually occurrence of this volume V. Okay. So this is our overall representative. So though individually our liquid portion and vapor portion are pointing towards the saturated liquid and saturated vapor line only, but this V is nothing but a representative magnitude of the overall specific volume depending upon the weighted average which is taken based on the dryness fraction. Okay. So you can see over here that our overall value will be lying in between our liquid vapor dome. Okay. Now one important thing we can do, our specific volume is nothing but equal to 1 minus x times VL plus x times VG. So what I can do over here, I can actually take this x common. If I am taking x common, I can write V is nothing but equal to VL plus x times Vg minus VL. Okay. So this Vg minus VL will be nothing but, this is my Vg and this is my VL. So this difference over here, whatever I will be getting, that is nothing but my Vg minus VL, and Vg minus VL is normally known as VGL. So when we are writing VGL, it means that we are actually taking the difference between Vg minus VL. So I can simply write my specific volume equation as nothing but equal to specific volume of liquid phase plus X times Vg into L, where VGL is nothing but Vg minus VL. Okay. So this is like what we have done in the two-phase region. If we have to define overall property of the system, this type of weighted average we do. So this type of weighted average is actually applicable for all the properties. So for example, if I have to write for internal energy at this particular location, so my internal energy U will be nothing but equal to UL plus X times UGL, where this UGL will be nothing but equal to UG minus UL. Okay, so you know that small u we refer to nothing but our specific internal energy. Then what I am now trying to say, is that whatever the weighted average I have shown for specific volume, that same type of weighted average is actually applicable for each and every property. Okay. Now, one small discussion I want to make over here. Yesterday there was one question in doubt clearing session, so I thought to take it over here. The question was that I have given you the idea that we are having some substances which actually freezes upon freezing expands. Okay, so for example, we are having water as a very common substance which while freezes it actually expands. Okay, so what is the reason for that? So the reason for that is we know that while we are having water molecule, we have actually oxygen and hydrogen atoms. Okay, so while we have water molecule in particularly liquid phase, during that time our molecules are randomly oriented. So though during that time we may have formation of some hydrogen bonds, but still molecules will be randomly oriented and they can actually interact in between, and we will be having less void spaces. Okay, so as we are not having very sequential or systematic arrangement of the molecules, so that's why we will be having actually less void spaces in case of liquid, and molecules will be close to each other. Okay, and if the same mass of liquid I convert it into solid, so it means I will be now organizing the same number of molecules, because mass I am taking same. So if mass I am taking same, all my number of molecules will be same. Okay, so because of that, what will be happening now, while I will be shifting from liquid to solid phase, in that case now my molecules will be having actually some proper crystal arrangement. Okay, so because of that proper crystal arrangement, now we will be finding that while we will be having the formation of hydrogen bonds between the molecules, because of the proper crystal arrangement and because of the hydrogen bonds, now our molecules will be arranged in such a fashion so that we are having actually large void spaces in between the molecules. Okay, so we will be having nothing but large voids in case of solids. Okay, so that is the reason that, because in case of conversion of water from liquid to solid, we will be having some proper crystalline arrangement. So while molecules will be orienting in the crystalline arrangement, there will be formation of hydrogen bond in between the hydrogen atoms, and the formation of hydrogen atoms in combination with the proper crystalline arrangement will lead to a situation where we are having large voids between the multiple between the subsequent molecules. Okay, so that's why we will be having actually expansion of substance in case of solid, and in case of liquid, molecules can actually interact in between. Okay, now what I will do, I will now first briefly go with the slide in order to represent the two-phase region, and after that we will immediately go for our discussion of steam tables, where we will try to employ steam tables for obtaining the properties, thermodynamic properties of the steam. Okay, so what we are having, this is nothing but our two-phase region curve. So already I have told you that this particular line is corresponding to x equal to 0, and this particular line is corresponding to x equal to 1. Okay, and any property, if I am writing as VFG, so what they are doing, this particular book is actually using F instead of L. Okay, so this F symbol is nothing but referring to the saturated liquid for fluid part. So VFG they are writing as nothing but equal to Vg minus Vf. Okay, then you can clearly see this distance from here to here, that is our Vg minus Vf, and anything which we are writing as V minus Vf, that will be actually our this particular portion. Okay, so this diagram is nothing but the representation of our liquid vapor two phase region. Okay, then after that, we are having actually some tables which I have already uploaded on the Moodle. So these particular tables are actually known as steam table. But before going to the steam table, let me just briefly discuss one more concept. So what we are having one important rule. That important rule is actually called as Gibbs phase rule. Okay, so what Gibbs phase rule does? Gibbs phase rule tells us that when we are having actually some substance that and there are chances of occurrences of that substance in multiple phases, then this particular rule specifies that how many number of independent properties are required to define the state of the system. Okay, so this basically tells the number of independent properties which are required to specify the thermodynamic state of the system. Okay, so as per Gibbs phase rule, the number of properties we call as nothing but number of degrees of freedom F. So as per this, F is nothing but equal to C minus phi plus 2, where this C represents the number of components of which our actually system is comprised of, for which we want to define the property, and phi represents the number of phases present in our system. Okay, and F represents the numbers of degree of freedom. It means the number of independent properties which are required to specify the state of the system. Okay, so now let me take up few examples. Let us consider that we are having compressed or subcooled liquid. So what we are having, compressed or subcooled liquid. If we are having compressed or subcooled liquid, in that case what is happening?
Sir, sorry, sir, to interrupt you, but what the definition you said about Gibbs phase rule doesn't tally with the state postulates?
So
The number of independent properties to define the state of a system.
yes, it is something
On,
to, yeah, it is.
only thing in the state postulate was that intensive was also a term added in that state postulates, and here intensive word is not used. So are those different?
No, no, intensive, always while we will be defining the property of thermodynamic system, we will be always using the intensive properties only. Okay, so I am referring to property as intensive only. Okay.
No, sir. I'm saying, sir, is Gibbs phase rule and the state postulate, are those two same?
Yes, so what I will be doing, okay, so what we are doing in case of Gibbs phase rule, we are specifying that F is equal to C minus phi plus 2, where our F represents the number of degree of freedom. So that degree of freedom is nothing but number of independent properties which are required to specify the state of the thermodynamic system. Okay, and C is nothing but our number of components, and phi is nothing but our number of phases. Okay, so now I would like to demonstrate this particular rule with the help of one example, and in this particular example we will take up a case of some substance in compressed or subcooled liquid state. Okay, so if I take a substance in compressed liquid state, I'll be having how many number of components? Let me consider that I have water only as a substance. Okay, so if I talk about water, water is having only H2O molecule. So it means when I am taking water as substance, number of components in my system is nothing but equal to 1. Okay. And if I take compressed or subcooled state, in case of compressed or subcooled state, I will be having water always present in liquid phase. If water is always present in liquid phase, in that case my value of phi will be also 1, because we are having how many phases? We are having nothing but equal to 1 phase. Okay. So now if you try to find out f will comes out to be 1 minus 1 plus 2. And finally, we will be finding that we require nothing but two properties to specify the thermodynamic state of the system. Okay, so now if you relate this particular Gibbs phase rule, you will be finding that it is giving your number of independent properties which are required to specify the state of the system as identical to that of the state postulates. Okay, so whatever we have studied in state postulates, it is giving the same number of properties which are required to specify the state. Okay, now let me take up another example of superheated state. So now if we take superheated or rarefied state, in that case what will be happening? Once again, we will be having number of components as 1 only, because we are only considering water, and our phases are in the superheated state, phase will also be completely vapor, so phi will be 1. So once again if you calculate, we will be having 1 minus 1 plus 2 as nothing but equal to 2. Okay, so in case of superheated regime also we require two properties to specify the state. Now if we talk about saturated liquid or saturated vapor. Okay, so let me write, if I take either saturated liquid or say saturated, or I simply write saturated state. Okay, so if I take saturated state, in case of saturated state, what will be happening? Number of component is 1 only, because we are having only water. Whether we are going into vapor phase or in liquid phase, everywhere we will be having water only. Okay, so number of component is 1 and phi represents the number of phases. Now in case of saturated state, our substance can exist either in liquid phase or it can exist in vapor phase, or it may have mixture of liquid and vapor also. Okay, so it means that for saturated state, our component can exist in multiple phases. If our component can exist in multiple phases, so value of phi, and what are the phases? It can exist liquid and vapor. So it means it can exist in two different phases. So value of phi will be 2. So that's why what will be happening now, if I calculate f, it will be nothing but 1 minus 2 plus 2. So it means if we have any substance either in saturated liquid state or in saturated vapor state, we require only one independent property, one intensive property to specify its state. Okay, so that will be only true when we are only interested in knowing the property either in the saturated liquid state or in the saturated vapor state. Okay, and if we have mixture, of liquid plus vapor, so in case of a mixture where we are having actually the combination of liquid and vapor, what will be happening? We will be having actually requirement of, because if we only take a single property, with single property we can determine, because say as I have already told you that if I have this temperature and specific volume, and this is my TV diagram, and if I take any temperature value and corresponding to that temperature, by just knowing the temperature, I can define value at this particular point also, okay, and I can define value at this particular point also. So it means by just knowing the single property, I can define the state either at saturated liquid or saturated vapor state. Okay, so that is something which I can do by just knowing a single property, and along with the single property we are also knowing one additional thing, that our substance is nothing but in saturated state. Okay, so if we are knowing this much information, that we are having saturated state and our we are knowing a single property, I can specify the states. You can clearly see from this TV diagram. If I know temperature, I can find out the value of specific volume. If I know specific volume, I can find out the value of temperature. Moreover, I'll be knowing about the pressure value of this one. Okay, so whatever the constant pressure line we are having on this TV plot. So it means by just knowing a single value and getting an idea that our substance is existing in saturated state, by this combination actually I can determine all other properties. However, if we have to determine the property in between the liquid vapor phase, so it means whether I need to point to this particular location or to this location or to this location. So that is something which we are not knowing. So that's why in case of mixture liquid vapor dome, we require one additional parameter in order to point at any specific locations in between the liquid vapor dome. Okay, so for the mixture we require actually one additional property, so that one additional property can be dryness fraction. So if you are able to directly measure, it can be simply your dryness fraction. Otherwise it can be that, say you are representing some overall specific volume as V, and that overall specific volume V, then you are actually converting it into then you are obtaining the value of X by using Vf plus X times Vfg. So okay, F I am over here referring to L. Okay, so this is how, like, we have to use this particular rule for determining that how many number of properties are required to specify the thermodynamic state of the system, or to determine other properties from the steam tables. Okay, so for example, if we are having a compressed or subcooled state, in that case what we have to do, we require two different properties in order to specify the state. Similarly, if we are having superheated state, there also we require two properties to specify the state. Okay, however, if we have only single property, if we have only saturated state, okay, whether and there we are only referring to either the liquid portion or the gas portion, there we require only one thermodynamic property to specify the state. And while we will be talking about the mixture, then in case of mixture, apart from the values of property at the saturation lines, we also need to define one additional parameter to specify the properties in between the liquid vapor dome. Okay, so now what we have certain tables, and these particular tables helps us in obtaining the values of different properties. Particularly for the case of water, these are known as steam tables. Okay, so such tables which represents the properties in different portions of the curve. For example, in solid liquid portion, liquid portion, liquid vapor regime, or in the vapor regime, these particular tables are actually called as property tables. And when we are talking about the property tables with specific to our particular fluid water, these are particularly known as steam tables. Okay, and these steam tables I have already shared with all of you on Moodle, and I hope you all have come up with steam table for today's lecture, because I have asked you, all of you, to come with the stream tables. Okay. So now, as I have told you that stream tables may be available in all the regions starting from solid phase to the vapor phase, but as in particular this course, our engineering thermodynamics, our majority of the discussions will be in the liquid vapor design. So that's why whatever the stream tables I'll be showing to you over here, we will be mainly concentrating ourselves in the liquid vapor region. Okay. So now let me show that how our steam table looks. So I have included some excerpts of the steam tables in our slides. Okay. So here you can see in this particular slide what I have saturated water temperature table. So the meaning of this particular table is that now we are referring to the saturated state. Okay. And as we know that if we are knowing the saturated state, then by just knowing one property, I can determine the value of all other properties. So that's why what we are doing, we are actually plotting over here the properties of saturated water by considering the temperature as our known parameter. Okay, so that's why I have written over here temperature table as my known parameter. Now, if I go through the different columns of this particular table, so you can see my first column is nothing but temperature. Okay, so this is the temperature, which is our first column, and then next column is actually saturation pressure corresponding to that temperature. So it means whatever the temperature we are taking, obviously we are referring that if we are pointing to the saturated water, so it means whatever the value of pressure we will be getting corresponding to this saturation table, that will be representing my saturation pressure. Okay, so let me once again explain you the concept of saturation pressure. So what I am referring to, that if I have TV diagram, in this TV diagram, this is my liquid vapor dome, and let me consider that this is my some constant pressure line P1, this is some another constant pressure line P2, okay, which is greater than P1. So now what will be happening, say if I am pointing to this temperature T, so say this is my temperature T1 which I am pointing to. So if I just take a straight line from this temperature T1, and if I see the point, the instant at which actually, or the location at which it crosses this saturated liquid curve, whatever the constant pressure line we are having corresponding to this particular point, that P1 will be nothing but my P sat at temperature T1. Okay. So what I am trying to say, that if I take this T1 and if I extend this T1 till my saturated liquid line, okay, so in that case what will be happening, the instant at which, or the location at which this constant T1 line will be crossing the saturated liquid curve, at that location whatever the constant pressure line we will be having, that particular constant pressure line I'll be calling as nothing but my P sat, and this P saturation will be corresponding to temperature T1. Similarly, say if I want to take now any temperature T2, so what I'll be doing, I'll be taking this constant temperature line till my saturated liquid curve, and at this now saturated liquid curve, whatever the pressure line will be passing through it, that pressure will be nothing but my P sat at this temperature T2. Okay. So this is what we call as nothing but our saturation pressure. So it means any property which I'll be defining on the saturated liquid line, that will be my saturated liquid property, and any property which I'll be defining on the saturated vapor line, that will be my saturated gas property. Okay. So now once again let us go to our steam table. So in case of this steam table, now what we are having, we have temperature as our first property. So corresponding to that temperature, whatever the saturation pressure we are having, that is also reported over here. Okay, and then next we are showing specific volume as one of our important property. So specific volume, now as I have already told you that for saturation state we may have existence of the component either in liquid phase or in vapor phase, or it may be mixture. So if our component is in liquid phase, then we will be having property as saturated liquid, which I am writing as Vf, and if I have saturated vapor, then my property will be Vg. Okay. Then another property we have internal energy. So internal energy is nothing but small u, and we call internal energy as overall internal energy, extensive internal energy per unit mass. So we will be having kilojoule per kg. Okay, so over here you can clearly see this small uf is referring to saturated liquid internal energy, and small ug is actually referring to saturated vapor internal energy, and this UFG over here is nothing but it refers to UG minus UF. Okay. Then similarly, we have one more property, enthalpy. So in thermodynamics, enthalpy is given by symbol H, and enthalpy is nothing but equal to small u plus P into V. Okay, so where small u is our internal energy, P is pressure, and V is specific volume. So for example, if you see for saturated liquid, whatever the value of H we are having, this H is nothing but this U plus value of pressure P times value of this specific volume of the liquid over here. Okay, so similarly we have this value of enthalpy for gas over here, and we are having HFG as nothing but my Hg minus Hf. So at the moment you simply remember that enthalpy is nothing but H equal to U plus PV. Now this PV component over here is something which is called as flow work, so that I will not elaborate at the moment. At the moment you simply remember that enthalpy is nothing but equal to internal energy plus PV. Okay. So we will have elaborate discussion on physical significance of enthalpy, particularly in our lecture when we will be talking about thermodynamic analysis of the open system. Okay. Then we have one more property which is called as entropy. So the unit of entropy is kilojoule per kg Kelvin. Okay. So we are having saturated entropy as SF, and saturated vapor entropy as Sg, and this over here represents Sg minus Sf. So entropy is also one of the very important property which we will be able to know or physically understand only after the discussion of second law of thermodynamics. So at the moment you can simply understand that whatever the value of entropy I am referring to, you are only concerned about the magnitude. Okay. Then one important point now I would like to highlight over here. So when we define any table, actually we set some reference. Okay. And with reference, actually our value of the property tends to 0. So similarly, in case of steam table, what we are having, triple point of the water is considered as reference for the steam table, and corresponding to triple point of water, the value of internal energy is actually taken as 0. So you can see over here we have the first point which is starting with a value of 0.01 degrees Celsius and pressure of 0.6117 kilopascals. So it means this temperature 0.01 degrees Celsius and 0.61 kilopascal is nothing but our triple point of water, and corresponding to this triple point of water we are saying that the energy content of that mass of water is equal to 0. So that's why we have specified the energy in the liquid state corresponding to this particular point as nothing but equal to 0. Okay, so it means the reference point of our steam table is nothing but our triple point of water. Okay. Now, if I had to determine say if I have to determine the internal energy of saturated liquid, say at temperature of 70 degrees Celsius. So what I will be doing, I know that if it is clearly given in the question that my state is in saturated liquid state and temperature is given as 70 degrees Celsius, so I will be simply pointing to 70 degrees Celsius, and corresponding to this 70 degrees Celsius, I will be finding that where is my internal energy, and internal energy I want to know for the saturated liquid, so I will be pointing to this particular value. So this particular value 293.04 kilojoule per kg, that will be nothing but my internal energy corresponding to this saturated liquid state at 70 degree Celsius. Similarly, if I say you have to find out, say at 85 degrees Celsius, you have to find out the entropy of gaseous phase. So you will be simply going to 85 degrees Celsius and you will be going to the saturated vapor, and then you will be pointing to the value of Sg corresponding to 85 degree Celsius. Okay, so this is how if we know the value of single property, we can be able to determine the other thermodynamic properties of the system. Okay, so for example, here if you are knowing about temperature and you are knowing whether your state is in saturated liquid or in saturated gas, you can simply determine the values of all the properties. Okay, so similar to this temperature table, we have one more table which is referred to as saturated water pressure table. So in this particular table, now instead of temperature, our first entry is nothing but pressure, and for different values of pressure, all the properties are specified. Okay, so now my question is to you that you have to determine value of enthalpy of gas corresponding to 30 degrees Celsius. Oh, sorry, corresponding to 30 kilopascals pressure. So if you have to refer to 30 kilopascals pressure, you will be going to enthalpy column, and in that enthalpy column, then you will be finding the enthalpy of gas as this particular value. Okay, so this will be my nothing but enthalpy of the gas. Similarly, what can happen, it is not the case always that we only require whatever the first property is given, that only can specify other states. It may also happen that I was given a condition that we are having saturated liquid state and enthalpy at the saturated liquid state is nothing but equal to 121.39 kilojoule per kg. Now we have to determine that what will be the saturation temperature, what will be the saturation pressure corresponding to this state. So if question is like this, in that case what I will be doing, the very first thing I will be doing, I will be going to enthalpy table, then I will be going to saturated liquid table, because along with the enthalpy it is given that we are having saturated liquid state. I will be going to saturated liquid table, and there I will be finding that where my value is 121.39, and the location at which I am able to find out the value 121.39, corresponding to that whatever the pressure, temperature, specific volumes I am having, that will be nothing but all my other thermodynamic properties. Okay, so it means if we are having the saturated table available, by knowing any of the properties and just knowing a keyword that whether it is in saturated liquid or saturated vapor state, we can determine all other thermodynamic properties. Okay, now apart from this, one important thing may also happen. Let us consider you are given a question that we are having saturated liquid state and the internal energy value is nothing but say 170 kilojoule per kg. Okay, so now if you refer to this table, so the question is we are having saturated liquid and internal energy is 170. So now if you see, go to the saturated liquid internal energy, you will not be finding value as 170. So what we have to do, we have to take this 168.74 and 191.79, and corresponding to that, say if I have to determine saturated pressure. So what I will be doing, first I will be finding the saturation pressure corresponding to 168.74, which is 7.5 kilopascal. Then I will be determining corresponding to 191, which is 10, and then after that I have to employ interpolation by considering the linear relationship in between the property parameters between 2 points. Okay, so let me just elaborate this one. So what I have nothing but I have to determine at 170, which is not available. So I have found close to 168 as my 7.5 and close to 191. These are the two closest point about 170. So here I have 10 bar, and corresponding to 170, I'll be saying, say my value of pressure is some P. Now I have to apply linear interpolation. So by using linear interpolation, I can write P minus 7.5 will be equal to 10 minus 7.5 divided by 191 minus 168 into 170 minus 168. So that is nothing but this I am taking as x1, x2, and corresponding to this pressure is my P1, P and P2. So we know the equation of straight line as nothing but equal to P minus P1 is equal to x2. So I have written this equation wrongly, because P minus P1 will be equal to nothing but x2 minus x1 divided by P2 minus P1 into, sorry, so this I am now I am writing it wrongly. Earlier I have written it correctly. So it will be nothing but my P minus P1 will be equal to P2 minus P1 divided by x2 minus x1 into x minus x1. So this is nothing but equation of straight line. So I am considering linear interpolation in between the two nearest points which are actually available if we have to determine the value of property exactly at our point of measurement. Okay, so now I will stop at this point and we will discuss further in our next lecture.